Hi, my name is Professor James. Welcome to this journey through space. Today we are going to study the chapter, which is Capstone Design, Simulate, and Optimize an Aircraft Component. In this chapter, we'll explore what capstone, design, simulate, and optimize an aircraft component are, how we detect them, the possibility of alien life, and the role of discovering new worlds. Course Overview. This capstone project gives you a real-world taste of aerospace design using computational tools. It's not just about theory, it's about building, testing, and optimizing a component that could exist on a real aircraft. You'll master CAD, FEA, and CFD tools, skills in high demand across the industry. Communication matters too, so you'll learn how to document your work professionally. Finally, your capstone becomes part of your portfolio, showing recruiters what you're truly capable of. Course objectives. By the end of this project, you should be confident using industry-standard tools. You'll tackle genuine design challenges, applying concepts from mechanics, fluid dynamics, and material science. Communication is emphasized. Your ability to explain engineering concepts visually and verbally matters. This isn't just for grades. It's your personal project to showcase in interviews. The journey will push your critical thinking and creativity. Learning outcomes. You'll learn to model in CAD, simulate with FEA and CFD, and interpret results accurately. Optimization is key. You won't just design something once, but improve it iteratively. You'll also learn how to assess simulation outputs critically and refine designs based on data. Your documentation must tell the story of your engineering decisions. These outcomes align with how engineers work in leading aerospace firms. Capstone Project Timeline. Your capstone is structured across 4 phases: component selection and CAD, FEA, and CFD simulation, optimization, and documentation. Weeks 1 to 2 focus on choosing a suitable aircraft component and modeling it. Weeks 3 to 5 dive into structural and aerodynamic simulations. Weeks 6 to 8 are about redesigning based on analysis. Weeks 9-10 wrap it all up with a polished presentation and peer review. Selecting your aircraft component. Choosing the right component is strategic. You want something that's challenging but doable, like an airfoil, structural member, or control surface. Consider components that are both structurally and aerodynamically relevant. You should be able to model it with the tools you have and find enough reference data to validate your work. This choice influences your entire project's direction. Component examples. An airfoil might focus on aerodynamic lift and drag, a structural member on stress under load, and a control surface on both. Each has its own challenges and simulation requirements. Some need high-fidelity CFD, others robust FEA. What you choose should let you demonstrate breadth and depth of skills. Be sure to match complexity with your comfort level and the available software. CAD modeling, getting started. CAD modeling is the foundation, your digital twin of the component. Tools like CATIA, SolidWorks, Fusion 360, or Siemens NX offer different advantages. Choose one you're familiar with or excited to learn. Accuracy is crucial, and your model needs to be simulation ready. Avoid unnecessary details that make simulation slow, but include all features that affect performance. CAD modeling. Best practices. Use real-world dimensions and data when possible. Keep your model parametric. It helps when you need to make quick iterations during optimization. Organize your design tree for readability and teamwork. Export in the right formats to ensure smooth import into simulation tools. Think of this model as the truth your simulations will depend on. CAD deliverables. You're expected to produce a full 3D model with technical drawings, mass property analysis, and a parametric version. The drawings should follow GD&T conventions. This mimics real industry documentation. Mass properties, like center of gravity, are essential in aerospace. You'll also need to show the component as part of an assembly, if relevant. These deliverables will form your first professional quality output. Structural analysis with FEA divides your model into small elements to simulate stress, strain, buckling, and more. You'll apply real loads and constraints to see how your component behaves under pressure. Modal analysis lets you understand vibrations, critical in aircraft. Fatigue and buckling give you a sense of long-term reliability. Tools like ANSYS, ABAX, or Nastran will be your playground here. FEA workflow. The FEA process has 3 steps: pre-processing, solving, and post-processing. In pre-processing, you import CAD, assign materials, mesh the geometry, and apply boundary conditions. During solving, you run the simulation while monitoring convergence. Post-processing gives you stress maps and displacement data. This visual output helps pinpoint weaknesses. It's both a science and an art. FEA, critical considerations. Mesh quality is key. Too coarse, and results are inaccurate. Too fine, and simulations are slow. You'll need to balance realism and efficiency. Boundary conditions must reflect how the component connects to the aircraft. Don't over-constrain. Loading scenarios should include everyday use and extreme cases. Use accurate material models for your analysis. Flow simulation with CFD helps you understand how air moves around your part. You'll analyze lift, drag, flow separation, and more. Just like FEA, CFD has its own setup and validation challenges. Pressure distributions from CFD can feed into FEA. Software like Fluent, STAR, CCM+, or OpenFOAM can be used depending on your access. CFD workflow. Prepare your geometry by creating a flow domain and simplifying non-critical details. Meshing is more complex, especially near boundaries and surfaces. Then, set up the physics, flow type, turbulence model, and boundary conditions. Finally, run simulations, interpret flow patterns, and extract coefficients like lift and drag. CFD helps make your design more aerodynamic and efficient. CFD critical considerations. Just like in FEA, boundary conditions and mesh refinement matter. You must select turbulence models carefully. Use Y+ values and mesh quality checks to ensure accuracy. Visualize velocity fields and pressure zones. CFD is computation heavy, so make smart trade-offs between speed and accuracy. Integrating FEA and CFD insights. Advanced designs often require integrating FEA and CFD. For example, use pressure from CFD as input loads in FEA. Explore aeroelastic effects and even fluid structure interaction. This multi-physics mindset is how modern aerospace systems are engineered. Your design must perform well structurally and aerodynamically. Design optimization process. The goal is to improve your component based on simulation feedback. First, set objectives, maybe weight reduction or better lift. Then, identify parameters to tweak. Run new simulations and compare results. Keep refining until you meet your performance goals. Optimization techniques. Use parametric studies to test variable changes one at a time. Topology optimization can show you how to lighten the structure without weakening it. Genetic algorithms help find global optima in complex designs. These techniques show employers you understand both engineering and innovation. Documentation and reporting. Your final report should include a summary, methodology, results, and visuals. Charts, plots, and CAD renders are essential. Explain your thought process. Why did you choose this design path? What trade-offs were made? Think of this as your engineering story.